So what is the convergent boundary then? Coming together, perfect. So we're moving toward one another, we're colliding. And typically with this, you're going to have subduction. And the reason, now why do we get subduction?
Density.
How does one plate get subducted underneath another plate? Has to have a difference in density, right? One has to be more dense than the other. Now, when we think about plates, what types of plates do we have out there?
A bunch of types.
Now we have a bunch of plates, but how many different types?
Land one. We have two.
Two, right? We have ocean plates and we have continental plates. Those are our two plates. That's all we really have. We don't have any air plates, just land and water. Okay. So, think about all the ways that we can combine those. I can have an ocean colliding with another ocean.
Mm-hmm.
I can have an ocean colliding with a continent.
Mm-hmm.
Or, in the worst case scenario, I can have a continent colliding with another continent.
Yeah, I would like that.
So those are your three types of convergent boundaries. Now, each one of these, especially these two, are going to have nearly the same outcome. And logic should prevail here to be able to tell the difference between the two. Think about if I have ocean to ocean. Same diagram. And this fits in perfectly when we talk about the Marianas Trench. We watched the video on that. Twice. So what do I have right here?
Twice. A trench.
That's your trench. And guys, this is something you have to do on the test. I'm going to ask you to draw me a diagram and label the geologic features. You need to be able to tell me, this is my ocean crust. This is my ocean crust.
Nice.
We have a trench.
Volcano.
What is this entire region? What do we call that?
Subduction zone.
That's the subduction zone. And yet, what forms at the top?
Land.
Volcanoes. Now, normally we would call this a volcanic arc.
Volcanic
Because
arc.
typically when these collide, they tend to have this nice little curvature to them. We call this a volcanic arc. But now I want you to think about this, again, let your logic take over for a minute.
Alright.
What is sitting on top of the oceanic crust?
Water.
Water. What's sitting on top of this oceanic crust?
Water.
So what's happening to my volcanoes here? What are they surrounded by?
Water.
So what do we call those?
Islands.
Islands. So we call this a volcanic island chain.
Nice.
Because it's surrounded by
water.
water. And we have several places in the world today where we can find this.
Hawaii.
Hawaii is not an example of this.
Why not?
Hawaii is something we call a hot spot.
Okay.
It's a weak spot within the plate where the magma is able to go through the center of the plate. Normally when we have volcanoes, it is typically along a plate boundary, but there are a few rare spots where it happens in the middle of the plate. And Hawaii is one of them. Yellowstone National Park is another example where we have a hot spot in the center of a plate.
Gotcha.
So normally, with ocean to ocean, we get these volcanic island chains. In fact, you know, right here along the Aleutian Islands, you can see the deep sea trench,
Pretty cool.
where the ocean plate gets subducted underneath the Eurasian and North American plate, and then we have the island chain.
I'm not Asian. Pretty sure.
When we look at the East Pacific, you know, basically this comes back down like this. We can follow that back down all along the Japanese islands, back down to the Philippines, and then also along the Marianas Trench. So these are examples of where we have ocean-ocean colliding. And again, we have volcanic island chains that form as a result of that subduction.
It's better than continental.
Alright, now let's go into some logic here. Suppose this wasn't ocean. What if that was continental? How would this be different if that was continental crust?
Those wouldn't be islands.
They wouldn't be islands. What would we call those?
Volcanoes.
Yeah, volcanic mountain chains.
Oh, mountains.
And that's basically the only difference. Same exact setup. We still have our trench. We still have volcanoes, but now they're no longer islands. They're now mountains. So we still have our ocean crust. We have our continental crust. And again, the ocean is being subducted underneath the continental. Again, why is that?
Yes, ocean is dense.
Ocean is more dense because it's made out of what type of material?
Basalt.
Salt.
Granite.
Which is more dense than
Granite.
granite.
I remember something.
So where do we have volcanic mountain chains? I want you guys to think about that for a minute. Where do we have these chain of volcanic mountains? Coleman?
Or continental collide.
Okay, exactly, but where? I want you guys to give me some real world examples of this.
Washington, D.C.
State.
State.
Alps, not exactly.
Washington State.
Where at Washington State?
Top.
Come on, I need you to think a little bit more for me here. What do we call that mountain range over there?
Mount St.
Yeah, Mount St. Helens part of that, Mount Hood's example of that, Mount Rainier. These are all three major volcanoes along this particular section of the Rocky Mountains.
The northern.
They have a unique name to them.
The volcanic Rockies. No. I don't know. Sorry.
The ones that volcano.
I'm being facetious.
Somewhat correct, but wrong. They are kind of volcanoes, or they are volcanoes, but they're somewhat part of the Rockies. It's called the Cascades. In fact, so that whole chain goes all the way almost from the North Pole all the way down to the South Pole. We're going to see that here in a minute.
That's a big change.
So we're going to kind of see how these volcanoes form. As that ocean is being subducted, because the water comes in, makes it easier to melt the rocks down here. We start to have our volcanoes start to form. And like the islands, basically it's just going to follow along the same, notice the trench right here, it's going to follow the same shape of that trench. That's where I had pictures of that.
Ocean ID telling me examples like that.
Actually, no. But I did. Okay, so I'm going to draw a really crude shape here. Just give me a second.
Really guess what it is. Squirrel. Can we play charades?
Is this squirrel?
It's obviously a bird. It's a pterodactyl. You see the beak and like the pointy thing on the head.
It kind of looks like Mexico.
Wow, that's actually
Florida.
good.
It's
Like,
a cardinal.
It's the bottom of
It's,
the United
it's the
States.
USA.
It's a cardinal.
That's Baja California. That's Mexico.
I know he was.
That's Florida. That's
Okay.
Alaska.
It's a zebra.
Yeah, all right. So it's basically North. Yeah, all right. So really bad representation here. Sorry, not really great in art, but actually not too bad. This is definitely North America, and we have this volcanic mountain chain that literally goes all the way along the west coast, down through the isthmus, and then back down along the entire western coast of South America. And this creates one gigantic mountain chain that literally goes from pole to pole. In fact, we even have places here, it goes and wraps back up through northern Alaska. So where we basically start at the Brooks Range in northern Alaska, along the Cascades, through the Sierra Nevada, and then continues all the way down through Latin America, and then finally down through the Andes Mountains. And this is all one gigantic mountain chain that is formed, volcanic mountain chain that is formed by the Pacific Plate being subducted underneath the North American and South American plates.
They should just name it one mountain.
It should be like one mountain range. But the whole area mountains.
Now, when we have continental to continental, we have a little bit different impact here. It's basically like this. It's basically taking two semis and running them into one another.
That's pretty cool.
You too.
What is going to happen with that?
The big semi is going to go on.
Probably an explosion. Or they're the same size.
And they're just going to stay there. They're never going to do anything and stay there.
Pretty much. Okay, so
That
this is a question that Coleman came up with earlier. In between here, you can see where I had the oceanic crust. And what literally is happening is the ocean was sitting between the two continents. And as the continents were coming together, it's subducting the ocean on both sides. When finally these two plates merge, they've completely swallowed up the ocean, there's nothing left. And they're still coming together, there's only one place for them to go. They can't back up,
Don't go down.
so they collide and they
Go up.
get forced upward.
So like the mountains we watched the other day.
Like mounds of what?
The movie we watched the other day.
Yeah, what was that called?
I don't know.
Okay, that's the Alps, right? The perfect example where you have the African plate slamming into the Eurasian plate. And probably the best example of this today would be the Himalaya Mountains, where we have India colliding with Asia.
Yeah.
And that's why a lot of times in these areas we can see a lot of oceanic fossils.
There's probably a dead squid like on top of that. Like the jump.
I'm not going to find a fossil of a squid.
It's probably a squirrel.
I might find a fossil of their beak, but not the squid itself.
No, it's still alive. Like it's just.
Just chilling.
Yeah.
That'd be kind of weird.
I'm gonna take a squid there and then be like, this is a 1,000,000-year-old squid.
It's not carbon dated, so it's real.
Yeah.
It's all
So-
science has to say.
This picture here on the right is a picture of the Alps.
We are right.
And then you can, what's kind of neat, if you actually take a look at this picture of the Himalayas there on the left, it's a really neat image because it gives you a perfect view of the Asian plate, which is now part of the Tibetan Plateau, that has been forced upward because of the collision with India. And you can very clearly see that line that makes up the tropics of India. And as soon as we get above that, we now have a dry desert. By the way, why are deserts dry?
There's no water.
Why is there no water?
It doesn't rain.
Why is there no rain?
Because it's too dry.
No.
Clouds don't like it. Doesn't mountains do something?
Yeah, the mountains are involved.
They block the clouds. Just kidding, cloud.
No, they don't really block the clouds.
They collect the rain from the clouds.
It's something that we call orographic lift. And in orographic lift, the air builds up behind the mountains. So here's my big mountain, and the air comes in from the ocean, nice and moist, so a lot of moisture, a lot of rain, and it hits those mountains, and immediately it gets lifted upward. You can't really go through the mountains, so they get lifted up. And as they get lifted up, they cool, they condense, we get a lot of moisture, we get a lot of rain along this side. And as soon as that air is able to go up and over, all that rain has already fallen out of the air. So now we have a very dry air beyond the mountains. So when we think about the deserts of the United States, it's the same thing. You have the Rocky Mountains that are literally cutting off the moisture content to those areas. That's why we find deserts there. When we look at the deserts of China, you kind of got the same thing, where you have the Himalayas that are literally cutting off that moisture content coming out of the South Pacific. So a lot of times those mountains play a really big role in how we have deserts occurring on land. All right, I'm going to go ahead and take a pause real quick here. And finish up our notes. Oh, hold on, we're not ready to finish up yet. Got one more boundary to talk about. Whoop, too far. Transform boundary. Okay, we're making this really quick and simple. Transform